Hello and welcome to the Physics Olympiad. In order to help you prepare, we'd like to show you some interesting pieces of physics and how to solve some tricky question about that topic. We will start our series by talking about frictional forces between solid bodies. Very often friction is portrayed as an annoying phenomenon which you try to avoid. For example, when a ball is rolling on grass and we'd like to analyze the motion, frictional forces are responsible for stopping the ball's motion. However, friction can also be very useful. Imagine you try to walk. Well, you wouldn't be able to accelerate, decelerate or make a turn if there weren't frictional forces between your feet and the ground. A nail in a piece of wood wouldn't stay there if it weren't for frictional forces between the wood and the nail, which will keep it there. During this video, we'll limit ourselves to two cases of friction between solid bodies, which is static friction, when the two bodies don't move relatively to each other, and kinetic friction, when they do move or slide on each other. Let's first consider static friction. Static means that the bodies are not moving relatively to each other, so their relative speed is going to be zero. Now the magnitude of the frictional force is always going to be smaller than a certain amount. This amount is determined by the coefficient of static friction, which is a number which tells you how hard it is to make something slip on a surface. Imagine a rubber tire on a road. This is very difficult to make slip, so in this case, typically the coefficient of static friction is around 1. It could be a little bit higher than 1 even. In a case where it's very easy to make something slip, for example your feet on ice, it's easy to slip, so in that case you would have a μs which is more around 0.1 or even lower than that, but it can't go lower than 0. The other factor that comes into play is going to be the normal force, the force acting normally to the surface, and we'll see what that means in a minute. So in most cases you're going to be asked what the edge case is. So what kind of frictional force is in play just before the body starts slipping. So in that case you're going to be looking for the frictional force which is equal to the static coefficient of friction times the force acting normally to the surface. Let's take an example. Imagine a body that is resting on a horizontal surface. The body is supposed to have a mass m, which we just for example put to 1 kilogram, and we'll suppose that the surfaces are such that there's a coefficient of static friction between them which is 0.5. And we'd like to know what the magnitude of the force is that we can apply so that the body just does not start slipping, just at the limit. Now, if it doesn't start slipping, this means that there's a force which is exactly counteracting a frictional force, which is exactly the opposite of our accelerating force. And this comes from a force acting normally to the surface. What other forces are in play here? Well, since it has a mass, we know that on Earth it's going to have a certain weight, Fg, which is pulling it down, but it's not going into the ground. So there's another force, the reaction of the ground, which counteracts the weight, and that's what we call the force acting normally to the surface. In this case, since it's exactly counteracting the weight, in magnitude they are going to be equal. So we know that the force acting normally to the surface in this case is going to be 10 newtons in magnitude. Now if we apply our formula, F equals μs times Fn, in this example it's going to be 0.5 times 10 newtons, and this tells us that our force F at the maximum could be 5 newtons before the block starts slipping. Now let's talk about kinetic friction. Kinetic means that the speed can't be zero in this case, so the body is moving relatively to the surface. The magnitude of the frictional force is this time exactly a certain amount. It's not smaller than a certain amount, but it's exactly this amount. It's given by the coefficient of kinetic friction times the magnitude of the force acting normally to the surface. Imagine the example from before. We have a body on a flat surface, a horizontal surface, and it is moving to the left. So it is slipping on this surface. And we'd like to know what kind of force do we have to apply in order to keep the body moving at a constant speed. This means that our force needs to counteract the frictional force exactly. So this is going to be minus F. And once again, the weight is pulling the body down, but it's not going into the ground because the ground is reacting with a normal force which is exactly equal to minus Fg in this case where we are on a horizontal plane. Now the coefficient of kinetic friction looks the same as the static friction, but it's slightly different. In fact, we know that the coefficient of kinetic friction for a given surface is always going to be lower than the coefficient of static friction. This means that it's always more difficult to get a body to start sliding than to keep it sliding. Let's apply what we've seen to this example, question 13 in the qualification round of 2018. In this case, we have 4 masses which are either stacked on top of each other or connected by a piece of string, and we're pulling on them with a force F to the right. Now it's a good idea to give them names, and this is going to be mass 1, mass 2, mass 3 on top here, and then mass 4 over here. And we're going to suppose that there's no friction with the ground, but there's only going to be friction on these interfaces between the different masses. And we need to know what is the maximum force that we can apply before there's going to be slippage on either the interface between 1 and 2 or the interface between 3 and 4. Let's see what we can find out about the frictional forces here. On the first interface, there's going to be a static friction, so let's write that down. There's going to be static friction F1 and 2, which is smaller or equal than the coefficient of static friction on this surface times the force acting normally on the surface. Well, that's simply going to be the weight of the small mass, so Fg2, which is equal to m times g. So we know that the frictional force needs to be smaller than mu mg. What is happening on the other interface where we have frictional forces? Well, in this case, there's going to be a frictional force between 3 and 4, which is going to be smaller than mu times the force acting normally. Once again, since it's the same small mass m, which has a weight Fg3, which is again equal to m times g, so we can simply write mg. So the maximal force which is available on these interfaces is always mu mg in this case. So we need to find out on which surface there's going to be slippage, if there's going to be slippage. In order to find that out, we need to consider the different systems and different forces in play here. If we just say that the system we're analyzing is all the 4 masses together, and there's only one force that's acting on this that has an effect, and that is F. The vertical forces in this case are simply cancelling each other out. So we know that there's one external force here, F, and that needs to be equal to mass times acceleration. So we have 2 small m plus 2 big M times the acceleration of all the masses. If we select a different system, let's say masses 2, 3 and 4, well, in this case, the force responsible for their acceleration, that's going to be the frictional force Ff between 1 and 2. So we can write down that the frictional force between 1 and 2 is responsible for the mass times acceleration, so 2 times m plus m times the same acceleration as before. Let's consider another system. Let's only say, well, we have masses 3 and 4 in our system. the force responsible for their acceleration is going to be the tension in the string. Let's say Ft. Well, Ft is responsible for the acceleration of mass m, and they have the same acceleration as before. And finally, we have mass 4 that is going to be accelerated by the frictional force between 3 and 4. So the frictional force between 3 and 4 is responsible for the acceleration of m times a. And if we look at these two equations where the frictional forces come into play, we see that the blue one, F between 1 and 2, needs to be bigger than this one. So if there's going to be slippage, it's going to be at the interface between 1 and 2. This means that the frictional force between 1 and 2 can also be put equal to the edge case, which is mu times mg in this case. Now this gives you an equation where you can solve for A and plug this in the first equation, which is going to show you that answer B is going to be the correct one. Thank you very much for watching. I hope you enjoyed it, and I wish you the best of luck for the competition.